In exercise 12.11, we're trying to accomplish a multi-step synthesis. And when we see these molecules, you'll note one thing that should stand out to you now is how the carbon chain is different. On the left, you have a 5-membered carbon ring, a sort of cyclopentane, and you have that on the right too. On the left, you have a methyl group, and that's on the right too. But on the left, you only have 2 carbons in your other carbon chain, in the other carbon chain, and on the right you have 1, 2, 3, 4 carbons in that chain. So we've added these 2 carbons. Now that immediately tells us that one thing we're going to have to do is add a terminal alkyne with sodium amide to make it a nucleophile. We'll have to add that to an alkyl halide. As we've seen several times now, those two combined, this turns into a nucleophile, this has a leaving group on it, you can do an SN2 reaction. That's the only way we've learned in Organic Chemistry 1 for how to make a new carbon-to-carbon bond. And here we have a carbon-to-carbon bond here formed between carbons 2 and 3. So that's one thing, one piece of evidence we can get from just by looking at these structures. The other thing we see is that we have a couple other changes. We have this OH on carbon number 1, and it goes away. If something goes away, that's a sign of an elimination reaction. And on the other hand, we have this OH, we have that OH just appearing. And that probably means it's going to have to be added onto it in addition reaction. So these are some, and here, let me actually do that in a different color. These are some ideas for how to, for reactions that we'll need to do to make this transformation happen. Okay, well, one that we found really productive so far is this terminal alkyne one. Now, we look at our original molecule, and it could either be the terminal alkyne itself or the alkyl halide. So we know we're going to have to add 2 carbons. Should we add 2 carbons with a leaving group, or should we add the 2 carbons as the alkyne that we add? So these would be like carbons options for carbons 3 and 4. What we notice is that the reactive part of the molecule at the end is on carbon 4. And so you will want to have this triple bond on carbon 4 so that you can use those extra electrons to create this reactive group through an addition reaction. So we want carbons 3 and 4 to be the terminal alkyne. Oops. And we want this original molecule to be the alkyl halide. Well, that's convenient. So that's convenient because we have to do an elimination there. So we can do an elimination to get rid of this OH and create a pi bond. And then we can add a halogen onto that second carbon. Now, hydroxide is a terrible leaving group. It's very unstable by itself. If it takes these electrons and tries to come off of the molecule, it ends up having a full negative charge. That's very unstable, and so it would just pop right back onto the molecule. So it's a really bad leaving group. We've seen twice already in this chapter how to turn an OH into a good leaving group. And that is to add TSCl followed by pyridine. TSCl is 4-toluene sulfonyl chloride. That's the technical name for it. And what it really does is turns the oxygen into a good leaving group. It's a big, long structure. We've gone through a long explanation for it in a previous video in this chapter, so I don't want to spend our time right now going through that. I would refer you back to that previous video in this chapter, but the result is that you have this TSO, this tosylate group, and that is a good leaving group. So if you need to turn an OH into a good leaving group, you can add para-toluene sulfonyl chloride and pyridine. Once you have that good leaving group, we want to do the elimination reaction. And we want the pi bond to form toward the right, right? The leaving group, the carbon that has the leaving group on it is the alpha carbon, and each of the carbons next door to that is a beta carbon. So we could do two possible elimination reactions. We could either take the leaving group off and form the pi bond between the alpha carbon and the beta carbon on the left, although actually we can't do that because this carbon already has 8 electrons around it and there's no hydrogen here for the base to steal, so we wouldn't be able to make that anyway. Or we could make the elimination to the other beta carbon. And that's the one we want, because we want to make the alkyl halide there. Well, I should do that in blue. We want to add an alkyl halide onto that carbon so that our terminal alkyne could attack it and attach. Well, to do that elimination reaction, you're trying to form the pi bond in the direction of the less substituted, less crowded carbon. What would prefer a less crowded hydrogen? Less to steal? A bulky base, so potassium tert butoxide. Now in this particular case, because there is only one beta hydrogen, you could technically use any base. But just to get in the habit of thinking of how to create a pi bond toward a less crowded area, we could use a bulky base like potassium tert butoxide. Once you have that, we can finally put our halogen on that carbon. So we want to get that, we want to turn that into this. Because if we have that leaving group on carbon number 2, then carbon number 3 here can come in as a nucleophile and replace it, and we would have this connection. Okay, now we added two things here. We added the bromine for sure, but we also added a hydrogen on the other carbon. In other words, we added HBr. The question is, did we add it Markovnikov or anti-Markovnikov? Let's look at the positions that each of those groups are on. The carbon that the hydrogen is on is bonded to 2 other carbons, so it is secondary. The carbon that the bromine is on is only bonded to 1 other carbon, so it is primary. The hydrogen went to the more crowded, more substituted position. That is anti-Markovnikov addition, and so you'd want to add peroxides here to make sure that you get that anti-Markovnikov addition. So that would give you that product. Once you have that, you can take this alkyne that we said we would be using, and you can mix it with sodium amide. And the sodium amide will rip off the hydrogen here. The electrons will snap back onto that carbon, and you'll create a carbon nucleophile. Now really, you would want just one equivalent here, so you don't rip the other hydrogen off also. And once you have that, you can do the SN2 reaction. This swoops in, attacks the carbon, kicks the leaving group off, and now we have, let me just make some room here. Now we have this molecule. So the bromine will be replaced by, where the bromine was, we'll now have this triple bond. So, we had carbon 1 and 2, we added carbon 3 and 4. So we have this chain now. And we did that, just to quickly recap, we did that by doing an elimination reaction. So we turned the OH into a good leaving group by adding TSCl and pyridine. That good leaving group we eliminated using a base. Because we wanted it to go to the less crowded area, we used potassium terbutoxide. Then we added a bromine on anti-Markovnikov. That gave us our alkyl halide. We reacted that with our terminal alkyne, and we got the carbon chain that we need. So now we just have to worry about the functional groups. We need an OH on carbon number 4, and we need to get rid of these pi bonds. Well, so if we look at these, carbon number 3 is bonded to 2 other carbons. So it is secondary. Carbon number 4 is only bonded to 1 other carbon, so it is primary. We want to add an OH onto the less substituted carbon. That's anti-Markovnikov addition. And so you would think, I could get that product if I did hydroboration oxidation. If you treat this with BH3 gas, stabilized by tetrahydrofuran, that's a gas, or you could use the solid 9-BBN, and you follow that up with H2O2 and sodium hydroxide. That would do anti-Markovnikov addition of H and OH. Now the thing is, that only works the way we want it to here if you have an alkene. So if you have an alkene, then you can do that. If you try to do this reaction on an alkyne, you'll end up with an aldehyde. The OH you would have, if you try to do it on an alkyne, you would have the OH adding here. This is an enol, and it would keto-enol tautomerize and leave you with an aldehyde, which would look like that. Well, that's not what we want. We want an alcohol. So we can't do that reaction on the alkyne that we have. We need to do it on an alkene. So we have to turn our alkyne into an alkene. And because this alkene is neither cis nor trans, it doesn't matter how we do this, just so long as we don't use just pure hydrogen gas and platinum, palladium, or nickel. We could either use hydrogen gas and Lindlar's catalyst. That would normally give us a cis alkene. Or we could use dissolving metal reduction, so solid sodium and liquid ammonia. That would normally give us a trans alkene. But either of those would give us an alkene, and so because cis and trans doesn't exist in that double bond, we could use either of them. Once we have the alkene, we could do the anti-Markovnikov addition of H and OH to give us our product. Okay, so let's recap. When we compared the reactants to the products, what we saw is that the product had more carbons. Now the way we knew how to do that was to add a terminal alkyne with sodium amide and an alkyl halide. That's the only way to add carbons onto a chain. But for that, we needed both an alkyne and an alkyl halide. We saw that in the product, the reactive part of the molecule was on the part that still had to be added. That gave us a hint that that part should be the alkyne. The pi bonds in the alkyne is extramolecular glue that we could do reactions with. So if we ultimately wanted something on carbon number 4, it would be useful to have extra electrons on carbon number 4 to play with. So that's how we knew that we would need an alkyne there, and that this other molecule would have to be turned into an alkyl halide. The bond we're forming is between carbons 2 and 3, so we need the halogen to be on carbon 2. We eliminated this OH. First we had to turn it into a good leaving group with TSCl and pyridine, and then we used a bulky base to create the pi bond toward the less crowded carbon. Once we had that, we did anti-Markovnikov addition of H and Br, and that put the halogen on that less substituted carbon there. We had that, and we reacted it with acetylene, ethyne. We just turned it into a nucleophile by treating it with sodium amide. So it did an SN2 reaction, and it gave us the carbon chain that we wanted. So now we had this carbon chain, but we needed to put the OH on carbon number 4. We noticed that carbon number 4 was the less substituted carbon, and the hydrogen went on the more substituted carbon. So that was anti-Markovnikov addition. But we couldn't do, and so anti-Markovnikov addition of H and OH is hydroboration oxidation. But we couldn't do the hydroboration oxidation on the alkyne because it would have given us an enol that would tautomerize into an aldehyde. And here we want an alcohol, not an aldehyde. So we hydrogenated the alkyne either with H2 and Lindlar's catalyst or with solid sodium and liquid ammonia. And once we had the alkene that we get after that, then we did the hydroboration oxidation and added the H and OH anti-Markovnikov. So altogether, if someone wanted to do this transformation, you would write this recipe down into a note for them. First, treat your alcohol, your starting molecule, with TSCl and pyridine. Then, add potassium tert-butoxide. Then, add HBr and peroxides. That gives you your alkyl halide. Mix that with some ethyne that you've treated with sodium amide. That'll do the SN2 reaction and give you the carbon chain you want. But you'll have an alkyne and you'll need an alkene, so, for example, you could use hydrogen gas and Lindlar's catalyst to turn the alkyne into an alkene. Lastly, you do hydroboration oxidation with the alkene, so you could use, for example, 9-BBN, followed by hydrogen peroxide and sodium hydroxide. And those beautiful artistic steps would allow you to create this transformation, or to achieve that transformation.